Welcome to the shop. Well, the glue is dry, and I think I'm just going to flatten out the surface of the piece before I go out to the CNC router and cut the inlay. Probably don't have to, but it's kind of nice to do and makes it just a little easier and cleaner to work with. So I'm going to be using this machine. This is a drum sander. And for those who have never seen a drum sander, it's an aluminum drum connected to a motor and a frame, and you wrap this sandpaper in a spiral pattern on the drum, and then the drum rotates and it sands the part. It's a useful machine, it works well. It does have a bit of a rigidity problem because it's got the end open here. Evidently the manufacturer has decided that being able to sand a wider piece in 2 passes is more important than having maximum rigidity. And, oh well, you know, if that's what the customers want, that's what the customers want. If I'm careful with it and use it within its limitations, I can hold a few thousandths on it. It's actually a machine that works quite well. You can see that it's hooked up to a dust collection system. If this machine is not connected to a dust collection system, the sandpaper will load up pretty much immediately and will not be a good thing. So, I seem to have lost my extension cord. I got the short cord blues. Ba-na-na-na, boom, boom, ba-na-na-na. Went out to the wood shop and tried to plug it in. Ba-na-na-na. Okay. Back in business again. So, dust collector on. Verify airflow. The last piece I did was thin, so I got to crank it up. Okay, there we go. Now it's off to the CNC router, and I'm going to cut that inlay pattern. Okay, I'm back at the CNC router, and I have the piece clamped in place. And before I start cutting, I think I'm going to do a little bit of cross-check, double-check, check again, check the check, measure twice, cut once, and just make sure this center point is really critical for the design. So I put a center finder tool in the spindle, and now I'm going to move to where the CNC believes is the center. And sure enough, I'm going to go down a little bit lower here. You can't be too careful, you know. I mean, it doesn't have to be within 1,000th. I don't have to get out the Heimer indicator to do it, but it is nice if it's, you know, if at least it looks like it's centered. So it looks like it's centered. I'm going to, I thought about this a little bit, and when I made my test piece out of MDF and dialed it in, I was tempted just to use that exact same tool path, but then I started thinking that there's a lot of dynamic stuff going on when cutting, and the wood reacts against the cutter, and who knows, things may bounce around or flex, or, you know, something may be weird. So I'm going to run the tool path as originally programmed without the last time that I cut the test piece, I kind of snuck up on it. And so I started with the original program and then moved in 5 and then moved in 2 and then moved in 2 again. So now I'm going to start with the original program and see if it behaves the same way as the test piece. And if it does, then I'll go ahead and run the program as modified during the test. So here we go. I've got everything on the network, so it's really convenient, like super convenient. When I got my Bridgeport for the first time, the Analam controller that it came with, the obsolete Analam controller, came with a, believe it or not, a floppy drive. And floppy drives don't last long in the machine shop, I tell you. So I replaced it with a USB drive, and that kind of helped a little bit. I couldn't find a retrofit network interface that worked in a system designed for a floppy. So anyway, Analam is gone. I'm now all on the network. Got to stop talking and pay attention. This is important. Here we go. Finger on the stop button. This dust is nowhere near as bad as the MDF dust, but, you know, the machine still makes a mess. This dust doesn't get quite as airborne as the MDF dust. And it looks like I'm getting a very, very nice cut with no tear out. Cut looks beautiful. Ramping in. Nice red dust. Don't you love it? Got a tiny tear out on that corner. I believe it will be okay. I believe I'll be able to deal with it. Okay. So, for those that watched the aluminum machining video where I talked about my artistic style, well, my artistic style is 50s atomic age. And part of the 50s atomic age style, which of course is inspired by aircraft design, is regular arrays of geometric holes arranged in a pattern. So now I'm going to switch to the 1/4 inch router bit here. Reset the Z height. And I'm going to cut some holes. The hole, and nothing but the hole, so help me hole. Finger on the stop button. That is not right. That is not right for 2 reasons. Off to the CAD room. Okay, let's try that again. Don't need to measure the tool position because it should be good. Tool hasn't changed. So I'm going to disable the tool change. Finger on the stop button. Yes, looking good. I want to be kind of careful with this guy. Do it in 3 passes. Relatively slow feed rate. After all this work, I don't want to booger it now. This is a solid carbide, 1/4 inch. I think it's a upcut spiral. .25,000 RPM, 30 inches per minute. 10 inches per minute plunge and 3 passes. I'm doing a depth of cut here of 300 thousandths, 0.3 inches. My final dimension will be a 1/4 inch, 250, and so I'm leaving a little for the bandsaw work, the sanding work, whatever else I need to do to adjust it. Boy, look at those holes. Holy hole, Batman. And no, the holes will not stay holes. The holes will be filled with inlays, precisely fitted inlays of a contrasting color wood. And that will be my next operation after this operation is complete. And then the glass pieces will be inlaid as well, which is somewhat challenging because they aren't geometrically perfect. So I have to kind of match a tool path to some imperfect handmade glass. Everything is looking exactly as it should. We got happy holes. Round and happy. I'm very happy that I have one tiny, tiny, tiny microscopic little sliver of tear out that will be no problem. I'll glue it back in place and it's still attached. But other than that, things are going very well. You never can tell. The tool path claims that it does things in some sort of a rational order, but sometimes it seems like it's just all over. Do this one, then I'll do that one, then I'll go back and do this one, and back and do that one. And okay, so if this is repeatable, it should not fit. And yes, in fact, it does not fit, and it feels pretty close to the same that it felt when I tested the test piece. So I'm going to go ahead now that I have fairly good confidence here that the hardwood is behaving the same as the MDF, and I suspected it would. I really wasn't expecting the two to be greatly different, but hey, you know what they say, when you assume, you make an ass out of you and me. So try to avoid assuming, try to avoid speculating. I don't even have a speculum. How can I speculate without a speculum? So, going to load the identical toolpath from yesterday that produced a very nice result, and realize that the machine has a tool change macro that assumed the that assumed the z-axis tool setter was in a different position than it's in. Of course, all this will change when I finally get my automatic tool changer, hopefully fairly soon. Finger on the stop button. Boy, it sure would suck to have this thing fail now. That looks really good. Known trusted tool path. So now, let's find out. Perfect as can be, absolutely no wiggle whatsoever. I believe I will be able to deal with the microscopic little piece of chip out there, and I believe that is successful. So, next step in the process, gonna cut that off with the bandsaw. I might not show that because probably no need. I'd have to set the cameras up back at the bandsaw, and you've already seen the bandsaw once. So imagine that same thing you saw before, except with a different looking wood. So next step is going to be to prepare the blanks for the inlays that go inside the hexagon borders, and these inlays will have inlays cut into them that will fit the glass. So, see you later. Now that the first inlay has been completed, it's time to move on and do another section of inlay. This is going to be the little circular dots that go in the circular holes, and as usual, I'm going to do a test piece just to make sure the dimensions are correct before actually using my piece of hardwood. So when I get around to the hardwood, here's the wood that I'm going to be using. This is Wenge, which is also an African hardwood, and makes a nice contrast with the Padauk. I'm pretty sure it's Padauk. I use Padauk for the Inkwala handles, and when I first looked at the board, it looked like, yeah, maybe it isn't Padauk, maybe it's something else, maybe I forgot, but no, it's Padauk. I recognized the smell when I was cutting it and sanding it, so it's going to be Padauk and Wenge, which is the same combination of woods I used on my dining table. So I'm going to go over here and load up the pattern. Once again, the computer over here, and I don't know if you can see it from this point, but one of the nice things about Mach 3 is that it allows you to make a custom user interface, and so I made my own custom user interface that is so much more usable than the Mach 3 standard. Anyway, I've got my program loaded up. Mach 3 is running on a Windows 10 box, even though it is claimed that, oh no, Mach 3 doesn't run on Windows 10, you need Mach 4. Well, runs just fine on Windows 10 for me. And no, I'm not using the parallel port version. I'm using what's called the Ethernet Smooth Stepper. And I'm going to be setting reference 0 on the top of the test part, and then cut out a few of these dots. And based on previous experience, I'm pretty sure that I'll end up having to adjust the toolpath a bit. So here we go. It wouldn't be a day in the shop without making a mistake, and it's always the same mistake. This is work offset 1, this is work offset 2. Okay, wonder when I'll stop making that mistake. And speaking of mistakes, here's another one to avoid. Let me get this system back into position here. I incorrectly made the toolpath with work offset 1 when it should have been work offset 2. And there's a temptation here to say, well, hey, I already probed the tool length, and so I don't have to do it again. That would result in pain and failure, I tell you. I probed the Z offset for work offset 1, and work offset 2, nope, not so good. So the Ethernet Smooth Stepper just failed with an error message. And when that happens, I usually just shut the whole thing down, because the Ethernet Smooth Stepper is not actually in the computer box. It's in the controller box, and it probably likes a power on reset, so let's give that a power on reset. So after restarting, I'm homing the machine, and what's interesting about the homing operation, first of all, for those who aren't familiar with this kind of machine and don't understand what I'm talking about, an open loop stepper motor, when it's first powered on, doesn't know where it is. All it knows is move one step in this direction, move one step in this direction. It has no idea where 0 is. And so all of these machines of this type do what's called a homing operation, which is move slowly toward a switch, and then when the switch is triggered, define that point as usually 0, but often a different home location is specified in the configuration. Well, the good news about this CNC router is that it uses a Pepperl and Fuchs, which I believe is German, sounds German. It uses a Pepperl and Fuchs proximity sensor, which is claimed to be accurate within microns, which makes the machine very repeatable in its homing. The Tormach machine did not have an accurate homing sensor. It just had a mechanical switch with a little roller and a little ramp, and the little roller and the little ramp could get chips on them or scuzz, and you know, it homed kind of sorta. This machine homes really well. The mini mill homes really well. Somehow I suspect it's got the same sensors on it, and it homes really well. So another thing, talking about the Ethernet Smooth Stepper, which is a kind of an interesting little side story here for anyone who cares about side stories and the history of computer control using commodity computers. At one time, back in the old days, the original IBM PC used to have a parallel printer port. And the parallel printer port was a big fat cable that was expensive and hard to deal with, and people who just needed to print were oh so happy when USB came along because the cable is smaller and easier and more flexible and cheaper and more available. But the old school IBM parallel port had a kind of an advantage that you could repurpose it as a general purpose digital port and use it just to set bits under computer control. When I was designing prototype motion control systems back when I was working, I used to use the parallel port a lot because it was just a convenient way to control things using a computer. Well, two things happened. First of all, as the Windows operating system moved to a more protected version, and when I say protected, in the world of operating systems, the let me try that again. In the older, more simple operating system of like MS-DOS, and I purposely mispronounce it just because it's humorous, because DOS is 2 in Spanish, and DOS is, well, you know what it is in the illicit drug world. In the old MS-DOS world, you could, a user program could directly communicate with the hardware and just tell the parallel port, okay, set that bit, clear that bit. In the, and that is, it worked at the time because MS-DOS programs really only did one thing at a time, and the computers were really simple, and it really shouldn't even be called an operating system because it was so crude. When Windows NT first came along, the idea was we don't want programs writing directly to the hardware. If two programs tried directly communicating with the graphic card or the printer at the same time, chaos would ensue. And so the operating system instead said, we will control the parallel port, all you can do with it is print. So for guys like me who needed to use the parallel port for a machine control, we said, okay, I guess I'll have to write a kernel mode device driver or use another very, very strange and semi-undocumented hack known only to the most eel-eat of eel-eaters, where you could actually configure a hardware register on the chip to allow user mode access to particular I/O ports, and of course I use that one too. And then motherboard manufacturers stopped providing parallel ports. So now we had two problems that, well, the operating system makes it nearly impossible to use the parallel port, and there aren't any parallel ports. So fortunately, people came along and designed workarounds to that. Mach 3 was originally written to use the parallel port, and then some dude came along, probably very much like me, a small business guy who had the background in engineering to do it, and invented the thing called the Ethernet smooth stepper. Works perfectly almost every time, except when it doesn't. And of course, I think to myself, hey, if I had a whole bunch of spare time, I could do a better one. But I don't have spare time. Too many ideas, too little time. Okay, let's try it again. Finger on the stop button. Boy, that one is pretty close to hitting my... Yeah, that came uncomfortably close. Okay. Okay, for the purpose of testing here, I don't need to make them all. So, yep. The pattern is repeatable. The parts are too big. So, let me do what I always do. Off to the CAD room. Make them a little smaller. Okay. Yeah, it would be kind of cool if it worked the first time, but a little bit of... And now this time, I don't need to reset the tool height because I didn't change the work offset, didn't change the tool, didn't change the stock, and so I can disable tool change and just go directly to executing toolpath. And of course the first one is going to be null and void. So while this is cutting, I don't know if anybody is interested, but I'm halfway thinking that it might be fun to produce a series of video educational courses on basic CNC machining, how computers work. I could do a video series explaining pretty much from semiconductor physics through digital logic, through operating systems, how computers work. And maybe someday if I get the time, I'll do that. Too many ideas, too little time. Okay. Let's pop off one of these dotly dots and observe that it's a happy fit. Happy, happy, happy. Fit, fit, fit. And there we go. So toolpath has been verified. And I'm now going to take my piece of wenge, which I've got the piece of wenge glued to an MDF substrate, and using my wedge system here, for those who haven't seen this, if you didn't watch the first video, I'm using a wedge system, and the wedges are cut out of shim shingles. I don't know why they call them shim shingles. Maybe at one time woodworkers used to actually use roofing shingles for the purpose of shimming. But anyway, these are little wooden wedges that are jammed in place up against these blocks. And it produces a pretty good hold. And the nice thing about it is that all of the holding fixtures are made of wood, so if anything goes wrong, I'm not going to be running my router bits into metal fasteners. So material thickness has changed. I'm going to reset my zero because once again, reference zero for this tool path is top of part, and sometimes I use top of part, sometimes I use bottom of part, depending on what it is that I'm making and what I'm trying to accomplish. Both have their purposes. So, finger on the stop button. Looks like it's cutting nice and clean. Dust collector is still working very poorly. And yes, I did try actually building a dust collector for the machine. Worked very poorly. Using 10 inches per minute plunge rate, 30 inches per minute feed rate, 25,000 RPM on the air-cooled spindle, which is variable speed, variable frequency drive. Using a solid carbide router bit. Cutting 350 thousandths deep. My final inlay size is going to be 1/4 inch, but because there's going to be a lot of bandsawing and sanding and a lot of other work that goes on before the final assembly is finished, I like to have a little bit of extra. Now you might wonder, why am I using a 1/4 inch thick inlay when only the surface will be visible? It could have just as easily been a 50 thousandths thick piece of veneer. Well, it's easier to deal with 1/4 inch material. It's more stable. It is easier to handle without being so extra careful to not destroy it in the process of working with it. And so, yeah, if I was in production and trying to optimize material yield, I would do a lot thinner veneer and probably refine the process a lot more. But since it's a one-off, I'm only making one, and I'd hate to break the piece somewhere along in processing because it's too thin. Just keep it thick. Keep it easy. Well, I believe we had success. So that completes. Let me get the vacuum here. Suck it off butt good. And that is the inlay dots. So now, and there they are. Beautiful. And the tiny, tiny little bit of chip out on the top, like I said before, I make everything intentionally oversized and then sand it down to the final dimension, and that completely takes care of things like the tiny amount of chip out on the top. So that does it for this operation. Now it's off to the bandsaw, where I will separate the dots into their dotly individual pieces, glue them in place, and then come back to show what happens next. So see you later.